This is the GMAT's 41 Support Student Education Initiative Program. You are welcome to our physics class. I hope you're doing great. Well, as for me, I'm fine and very happy to meet you. This happens to be our very first topic in this subject, physics, in this program. And so I want to use this opportunity to appeal to you, friend, to talk about this program to your friends. Encourage them to contact us. We have our contact number here on the board so as to enroll in this program that has been specially designed in order to improve students' understanding of maths and science. In this video, we'll be looking at the topic quantities, units, and their measurement. Like we know, physics is a branch of science, and science generally deals with matter. Our aim in physics usually is to take measurement of quantities. Is that okay? How do we evaluate them? How do we calculate them? How do we measure them? So physics is more concerned about that. However, in this particular lesson, there are some objectives of interest, and that we have on the board here, that at the end of this lesson, you should be able to define fundamental quantities and give their examples. Also, you should be able to define derived quantities and give their examples. You should be able to state the units of fundamental and derived quantities. Then again, you should be able to list the various measuring instruments that you encounter or see in your laboratory, okay? Instruments especially used in measuring length, mass, and time. And finally, you should be able to convert from one unit to another unit of a given quantity. Just think, for instance, you're given a unit of length, say in centimeter. You should be able to convert it from centimeter to another unit like meter. So these are the focus, the objective of this particular lesson under this topic. To start with, what is fundamental quantity? First of all, I'd like you to think about that word fundamental. When you hear fundamental, it's an English word that points out to uniqueness, that something is one of its kind. I hope you get me right. That thing can stand alone without any other. That's what the word fundamental, alright? That's the idea it bears. Therefore, when we hear fundamental quantities, they are quantities that do not depend on other quantities for their definition, alright? They are independent of other quantities. Fundamental quantities are also known as base quantities. So take note of that. In case you hear base quantities, you should know that we are still talking about fundamental quantities. What are the examples of fundamental quantities? An organization known as the International System Organization has recommended seven base quantities, and these 7 base quantities, also known as fundamental quantities, you are expected to know them. In fact, memorize them, okay, because there happens to be these 7 of them and no other one. So what are these 7 examples of fundamental quantities? Here on the board we have them: length, we have mass, we have time, we have electric current, we have temperature. That temperature sometimes you see attached to it, thermodynamic temperature. We have amount of substance. Amount of substance you encounter in math, in chemistry, okay, where you deal with the moles. We're going to study all these things. And then of course the luminous intensity, which has to deal with the amount, alright, the rate of sunlight, okay, let's say light. So these are the 7 base quantities. Please, like I said, you're expected to memorize them. This is a standard that has been recommended. Now, out of these 7 fundamental quantities, there are these 3 I don't want us to joke with at all, please, because we are going to make use of them a lot in the study of not just physics, but other aspects of science. These are the first 3: length, mass, and time. As a matter of fact, in our next class, under this same topic, when we're going to deal with dimensional analysis, you will see that these 3 base quantities, length, mass, and time, will be our major focus for which we use in determining the dimension and per se unit of some other derived quantities. So please don't joke with them: length, mass, and time. Let us now look at derived quantities. Derived, just like the word goes, derived. It simply means we get them from somewhere. We obtain them from somewhere. And then when you obtain something from another, it means that that thing depends on the other. So simply put, derived quantities are those physical quantities that depend on other quantities for their definition. The other quantities they depend on are fundamental quantities. Is that okay? And there are so many examples of derived quantities. The list cannot be exhausted. We cannot mention them all. There are many of them, and as you continue in this study of physics and other sciences, you're going to encounter these quantities. Here on the board, we've got a few examples: area, volume, speed, velocity, acceleration. What about pressure? What about density? Talk about momentum, impulse. There are many of them. Is that okay? That are derived. Now we've explained what fundamental and derived quantities are. We are now going to turn our attention to the units of fundamental and derived quantities. Alright, now let us look at the units, SI unit of quantities, fundamental and derived quantities. Or think about SI unit, that is the System International Unit. These are actually standard of measurement in which our quantities are expressed. Units is very important in the study of science. Please take note. And sometimes I refer to them as soul names, alright, of quantities, because with the unit of a particular quantity, you can identify that, yes, this is the quantity we are talking about. Without units, things would be meaningless in the study of science, of course, engineering. Is that okay? Just think, for instance, if you tell me this thing is 20, maybe this bag is 20, that's a 20 watt. Alright, 20 watt. But if you tell me 20 kilogram, I will know you are talking about the mass of that bag. Okay, just also imagine this example. You tell me that from here to where you are is 50 meter. Alright, immediately you say 50 meter, I will know that you're talking about length because of that meter. So SI units are simply standard of measurement, alright, standard values in which our quantities are expressed in. And the part here, we have the SI unit of fundamental quantities and some of derived quantities. Quickly, I want us to take a look at these units. Is that okay? Now on the board here for fundamental quantities, we have length, mass, time, and of course up to luminous intensity. Length, we use L for the symbol, right? SI unit is meter, we use M for it. Then mass, this is M, the symbol, and then the unit is kilogram, which is kg, we use kg for kilogram. Time, we can use capital letter, we can use small letter. Generally, this capital letter, we use them when dealing with dimensional analysis. Is that okay? We'll go to calculation aspect for like time, we use small letter for it. The unit is seconds, so we use S for that SI unit of time. Temperature, capital letter T symbol, the unit is Kelvin. K. Current, the symbol is I, unit is ampere, we use capital letter A for it. Amount of substance, alright, we use N for the symbol N. Small letter N, take note, not capital letter N. And then the SI unit is mole, M-O-L. Luminous intensity, I didn't include any symbol there, alright, it's okay. Now the SI unit is candela, C-D. Very important. So take note of them because these are the units we're going to use in obtaining those of derived quantities. Here on this part of the board, we have derived quantities. How we derive them, they are SI units. So quickly, area. Area is length times breadth. Please take note that breadth is still the same as length because the idea there is distance between 2 points. Even when you're talking about height, you're still referring to length. The only difference between using length and using height is length usually goes horizontally, while height goes what? Vertically. But both of them are still distance between 2 points. So they have the same unit as meter. And that is why in this case, area, which is length times breadth, the unit will now be meter, unit of length, times another meter, unit of length. And meter times meter will give us meter squared. Because in mathematics, indices, multiplication law of indices, if you're multiplying the same quantity, simply add their powers. So if you have meter raised to power 1 times meter raised to power 1, that will give us meter raised to power 2 when you add the 1 plus 1. It's actually a simple thing, okay? Now volume is length times breadth times height. I already explained that these things, they have the same units. So you multiply their unit, meter times meter times meter, and that's going to give us meter raised to power 3. We go to density. Density, mathematically, the formula is mass divided by volume. So that is how we derive it. It simply means that the unit of density is going to be the unit of mass, which is kilogram, over the unit of volume, which is meter cube. And that's why you have here kilogram over meter cube. We actually read this as kilogram per cubic meter or meter cube. Alright? This, using the knowledge of negative index law of indices, you can still write this in as kilogram meter raised to power minus 3. Okay? Velocity is displacement over time. Displacement is simply change in position. We're going to encounter that when we study motion. Change in position. So if I am at this point, which is this position, and I move, you agree with me that I have covered a certain distance, a certain length. So displacement shares the same unit as length. It means that velocity will be meter, which is unit of displacement, over time. The unit of time is second, so meter per second. You can also write it like this, ms raised to power minus 1, using the knowledge of negative index law of indices. Acceleration is another derived quantity I wrote here. The derivation is velocity over time. That's the formula. And so it's going to be unit of velocity divided by unit of time. And that's going to give us meter per square second. Because the unit of velocity is meter per second, then divided by unit of time, which is second. That per second in the numerator will step downward. If you're working out the mathematics, it's going to multiply the denominator second, giving you s raised to power 2. So everything will be meter per square second. Alright? So we have force, derivation. The formula of force is mass times acceleration. So of course it's going to be the unit of mass times the unit of acceleration, which is going to be kilogram times meter per square second. Now that kilogram meter per square second put together gives us what we call the Newton. The Newton. So the unit of force generally is Newton, capital letter N. Energy is the next one. Energy is force times distance. So it's going to be unit of force times unit of distance. Unit of force is Newton already, we said that. Then distance is meter. So we expect that the unit of energy is going to be Newton meter. That Newton meter put together is called the joule. And we use capital letter J for it. The last one I have here is work, is power. Okay, power. And power is work over time. Work is in joules because work and energy, they have the same formula, of course, and of course the same unit. Work is also force times distance, okay? We'll encounter all of these as we continue in this subject. So work over time will now be joule per second as a unit of power. This joule per second put together, we call it the watt. The watt. So we use this more in electrical studies. And then the symbol we use for watt is W. There are many other physical quantities that are derived. You can think of the momentum, like I said. Pressure. Like pressure is force over area. So we expect it to be Newton per square meter and many more other derived quantities.